This topic is about file geometry and the functional characteristics of different file geometries. Okay. So let's review a couple things. Standard K files. This guy has a handle on it. It's a 15K file. What is the geometry of a 15K file? Well, first off, the ISO color means we have a white handle. Okay, so the handle colors typically refer to the tip diameters. That is also tends to be true of many of the tapered files. And this number here is the diameter times 100, because they didn't want to put a little dot right there. Okay, so a 15 file is 0.15 millimeters. A 35 file, 0.35 millimeters, and so on. We don't talk about the taper because back in the days before we had variably tapered files, they were all the same taper, which was a very minor 0.02 millimeters per millimeter of taper. Okay, this is how we describe taper. Along the length of the file, we click back every millimeter from the tip, and the diameter of the file goes up by this amount. If we start with 0.15 millimeters at the tip, let's do the math. What do you think it is a millimeter back? It's 0.17. That would be 0.15, the tip diameter, plus the increase, 0.02, equals 0.17. We add up this latest plus that every time, so we get 0.19, 0.21, and so on. Okay, slow increase in diameter. We'll talk later about functional characteristics of different tapers, but I thought we need to start with what is the naming convention of the geometries and how do we describe the tapers. Okay, and in K files, we have both square and triangular cross sections. Now, back in the day, reamers used to be, most triangular files were typically called reamers. They had fewer twists along their length. K files were tighter, and these were used in a rotational cutting motion. These were used in a push-pull motion. Those distinctions are kind of beyond us now. We're not doing a lot of push-pull filing. So generally speaking, this is for small K files, 0.06. Sorry, I need to keep the decimal out of there. 06, 08, 10, and even maybe a 15K file. I want them square because they're so small. What I need in a small file is maximum strength and rigidity. As soon as I get to a 20 and up, I want less core diameter. I want more flexibility. And so you're going to find most of the 20 and larger, or I would choose them to be triangular. And you need to check with every manufacturer. They have several lines of K files. They could have a line that's square all the way up to the large sizes. But check it out and make your choices accordingly. Rotary files. Rotary files vary by tip diameter and by taper also, but we always describe the taper as well as the tip diameter because they're different. In K files, they were all the same. So tip diameters, anything you can imagine. Tapers typically 02, we'll even have rotary files with a narrow taper. 04, 06, 08, 10, and even 0.12. There's only one file that's really safely and successfully done that. That's the GT 0.12 accessory files. We'll get more into that later when we talk about maximum flute diameter limitation. But we choose the tapers we want to end up with. We use the tapers at different parts of the procedure to achieve different objectives. Okay, and we describe these as tip diameter first. Most companies do this. I think Cybron's the other way. We call it a 2004, a 3006, a 2510, whatever. Tip diameter and taper. Now there are some files that just have numbers, like a number 1, a shaping 1, a shaping 2. That may be a little more simple to describe, but I think it's not as good for dentists because I want dentists to know what the geometry of their instruments is, not that it's just the 1 or the 2, because that's going to inform them what's going on, why they feel what they feel in the canal, and what they should use next. It's based on the geometry of the existing file and the route that they're in. So first, what I've been talking about here is linear geometry. Linear geometry is what's going on to the geometry along the length of the instrument, whether it's a hand file or a rotary file that's got, you know, a latch grip on it. Okay. And as I've been mentioning, we're going to mention tip diameter, we're going to mention taper, and something new is we're, at least in some of the files, we're going to mention maximum flute diameter, or MFD. What does this mean? Most files have 16 millimeters of cutting flute. And that's fine. If you have an O2 taper, it starts at a 15, it ends up at you know, not a whole lot bigger than that. If we're using a 0.08 and larger taper, if you start out with a 20 tip diameter in an 08 file, we add 16 times 08 and it becomes, at 16 millimeters, it becomes huge. So even if we start out with a small tip diameter of 0.2 millimeters, if we go 16 millimeters back, at an 08 taper, we're adding 0.08 times 16, and that turns out to be a huge number. It turns out to be 1.28 millimeters. If this is a small root, that's too big for a small molar root. So the concept is we're going to start with whatever tip diameter and taper. We're going to extend it up, the geometry, the linear geometry at that starting point and that angle, and when we hit a certain maximum flute diameter, it could be 1, it could be 1.25, it could be 1.5, or anything in between, then the flute stops. So it's not always 16 millimeters. If we have a narrow taper like an 04, that's going to have something like 20 millimeters of cutting flute before we hit the 1 millimeter MFD of, say, the GT system or the GTX system. If we have an 08 taper and we start, say, with a 30, it's going to be much shorter, and it's going to be less than 16 millimeters. In the GT and GTX systems, this is for small roots. This is for medium roots, medium and large. And this is typically just for large roots. 1.5 millimeters is too big for these other root sizes. 1.25 millimeters, too big for most small roots, and 1 millimeter is really nice. It's very conservative. It's going to always keep you out of trouble in terms of furcal thinning and perforation potential, and it's a size that I've found that I can easily irrigate through and get really nice 3D obturation. So now let's talk about cross-sectional geometry. Okay, this gets more complicated and is continuing to get more complicated. As I said in an earlier topic, all these files start out with round wire. Typically take a piece of wire and they taper it first. They put it on a centerless grinder and they cut a taper in it, and then they put it into a fluting machine and they cut spiral flutes around its length, and the way they cut that will determine the cross-sectional geometry, obviously. If they cut flat lines to points, then we have a triangular file with a sharp cutting flute. The Pro Taper files, for instance, they have a convex triangle. And the concept here is this is very aggressive. And this is, so they're all 60 degrees. It's an equilateral triangle. When we pooch out the sidewalls there, we get closer to 70, maybe 72 degrees here. And that's going to reduce the tendency, the cutting edge to promote transportation. However, it increases the size of the core diameter of the instrument. So this turns out to be one of the stiffest files on the market. So in straight canals, big core diameters mean you're going to be really safe. You can honk on the files, probably can't break them unless they're really old. In curved canals, these things come apart in a heartbeat. The larger the core diameter, the more rapidly these instruments accumulate cyclic fatigue and come apart. And just as make a comment here so I don't forget it later, narrow files, they break due to torsional stresses. Wide taper files, they break due to cyclic fatigue. An example of this is your small negotiating instruments. Virtually every one you've ever broken probably broke because you rotated it more than 90 degrees in a clockwise direction. The blade tip hangs up and you just twist the rest of the instrument off because it's not strong enough to pull through there. However, narrow files such as the new path files that are rotary in an O2 taper can go around unbelievable curvatures because they're not going to come apart due to cyclic fatigue. Okay, so we get to landed versus non-landed. Okay. Here is a landed instrument. Here is the cross-section of a profile. These first instruments are Tulsa Dental Specialties, Profile, GT, and GTX. We also have a version of that with lands called a K3 by Cybron Endo. And it's a little hard to draw, but it looks something like this. There's a land here, and then it comes in and goes something like this. There's another land, and they are asymmetric. That's one of their chief design features. And this land here and this land here optimize, the objective is to optimize the cutting efficiency. Because if you have the sharp blades and you're spinning them at 300 RPM or worse, 600 RPM, they're going to rapidly open up curvatures. They're going to rip the end of it open to the outside of the curvature. They're going to transport to the inside of the curvature, run a risk of possibly perforating. When we make this slightly less efficient, less aggressive, or somewhat less aggressive, then it will tend to stay centered in the root canal. Lands require each of the blades. These two blades are riding on the dent and they're pushing on this blade to make it cut. And of course, these two are making this one cut, and so on. With this kind of a blade, the moment this blade touches any dentin, and it could be just on the inside of the curvature, for instance, we could have a file like this that's non-landed, and it'll be cutting right here, and it'll be cutting right here, and that's how transportation occurs. So the recommendation for non-landed files is you never cut to the same place twice. Every cut has to be to a new depth, or this is more likely to happen. This is a good instrument because the lands, it's a really stiff instrument because the core diameter. So great in straight roots, Not so good in curved canals. Okay. Let's talk about the non-landed ones. We've got straight triangle. The sequence file is theoretically has one low flute. They may have changed it, but the 3006 that I tested and did a CT scan and cross-sectioned it in computer space, it had actually one high flute. So it was even more dangerous than a triangular instrument. I'm sure that they fixed that by now. The Pro Taper, as I told you, look like this. They look like kind of a Wankel cam. So this is the cross-sectional geometry of a Pro Taper. And it's like the K3's got a large core diameter, slightly less cutting aggressiveness here. We also have other aggressive, different layers of aggression of instruments. We have some that actually have kind of a concavity to them. And the question is, are these good or bad kinds of blades to have? And the answer is that's the wrong question. The wrong question to ask is, where can we use these to their best to take advantage of their strong points and to avoid their weak points. Okay, and the answer here is gets back to how we transport. Okay, transportation. Transportation requires an aggressive blade usually. And it also requires stiffness of the blade. Okay. Without the stiffness, it's not pushed. These sharp blades aren't pushed against the outside and the inside of curvatures. So what this tells us is the non-landed blades, and this is huge, the non-landed blades, they're aggressive. The non-landed blades, we're going to use a small tip diameter and early in the procedure. Okay. We're going to do our initial cut with these. If we have, for instance, a 1506 razor sharp blade, this little guy here is so small that it's typically going to go to or near to length without transporting. If I use the same instrument in a 2506, I've had this experience, you know, one of those little curves at the end of a distal root and a lower molar, and a 2506 just ripped this thing out. I overfilled hugely. It's the only ripped apex I've had in like a decade. Okay, so not in the big tip sizes, yes in the small tip sizes. What we want in our apical prep and also our mid-canal prep and also our final coronal prep. Remember what I said before, I want one file landed to make the final prep from apex back to the orifice. Okay. But we need to understand that landed blades don't cut as efficiently, and some people get frustrated and let them stay in root canals too long, and they've seen them separate. So there's a misunderstanding that cutting fast is going to decrease your file breakage. So I'm talking about a landed finish. Okay, so what happens when we can't get our landed blades to length typically you have some kind of an S-curve, okay? Forcing a landed blade to length won't help at all, but we can use the balance force technique. Hand files, we can do literally 1 millimeter, 2 millimeter step backs. We could have a 20, 2 millimeters short, a 30, 3 millimeters short, a 40 could be 5 millimeters, 6 millimeters short. When we put a landed blade back in there, it's going to cut easier because we've relieved some of the binding with these K files. These are hand K files in nickel titanium. Okay. But if we use a landed instrument, and I've mentioned what those are, to get the final shape, we're going to have a closer fit to everything that follows. We are going to have the best opportunity for a system-based approach to everything else that follows. Because only with a landed blade finish instrument that cuts the whole length from the orifice to the terminus can we know what cone to fit.